20, right, in your class?
Yes, sir, 20.
So 18 I can find today. So it's good. Now let me first find out my file. So now hopefully we'll see something now.
Yes,
You
sir,
are
SG, sir.
seeing? Good. So now, see, today we are going to discuss method of images. Now, honestly speaking, method of images you have studied from your probably school level, particularly method of a point charge. I sorry, image of a point charge you must have done. So we are not going to discuss that. What we are going to discuss will be two practical examples and how we can analyze them with the help of method of images. And the first practical example is very well known in high voltage engineering called the sphere cap arrangement. Now, sphere cap arrangement, I am not sure whether you have seen it in the lab because of this pandemic and all that. It's a two metallic spheres, hollow spheres, and they are arranged either vertically or horizontally, and there is a certain gap distance between the two spheres, and of course it's natural air, atmospheric air between the two spheres. One of the sphere is typically at the high voltage, the other one is earth. This is the typical space sphere gap arrangement which is used in high voltage engineering extensively all over the world. This is used for measurement of voltage, this is used for calibration of equipment, and so on. And this is also used as a switch, very fast acting switch. Please remember this one. Uh, this is something I don't know whether somebody has told you or not. If you really require an extremely fast acting switch, which should operate of the order of microseconds, let's say a switch which should operate in 1 microsecond, and at the same time it should operate at a high voltage. What sort of switch I should take? Can you give an idea? A switch will operate at, let's say, 50 kV or 33 kV, and it should operate in 1 microsecond. What type of switch I can give? You cannot use circuit breakers and others. They operate in maximum half cycle, which is about 10 milliseconds. Any idea? Well, many of you probably will say solid state switches. Well, I don't disagree. Solid state switches can be used, but what is the voltage rating of one solid state switch? This you should tell me. If you take one, say, silicon switch or selenium switch, what will be its voltage rating? Because these are the information as an engineer you should have.
Sir, 3 to 30 volts.
3 to 30 volts. Any other idea? Well, nowadays you have very good switches. 3 to 30 volt is very low volt switches, which are typically used in particularly electronic circuits. But in power circuit, we can even go up to 3 kV. It is possible. They are available. But still 3 kV is not 33 kV. So then we have a problem in our lab. So in those cases, please remember this, sphere gap is the perfect switch. Because when the gap is not broken, that means there is no breakdown, this is open circuit. And natural air, that is atmospheric air, is the insulation. So you don't have to give any additional insulation. But as soon as the voltage reaches the breakdown voltage and the gap fires and the switch is on. And this breakdown of air is a completely electronic phenomena, and it happens within 1 microsecond. So therefore, this is an extremely good switch. Please remember this point, that typically we try to overlook this point. That sphere gap is not just a measurement or anything. It is also a very, very good, we call it fast acting high voltage switch. You cannot get a better switch than this one. So this sphere gap arrangement, can I analyze with the help of method of images? That's what today's first topic is, so that I give you a practical aspect of what you are discussing. Don't take it just as a mathematics. Mathematics or this sort of analysis is there, but this has practical implication. So first we are starting in this way that, let's say instead of two spheres, I am taking only the grounded sphere. You can see here the grounded sphere. And then I am saying that on this point at a certain distance d from the center of the sphere, I have plus q charge. This is my assumption. So now the question is, what I am trying to do is that, you know, a point charge plus q will always have an image with respect to the ground plane. But here, our ground plane is not the earth plane, but it's a grounded sphere. Can I have an image of plus q with respect to this grounded sphere? As a solution to that, what we are saying is, let's say this minus q, small q, as you can see, at a certain eccentricity from the center, and this eccentricity, this distance is s, you can see in the on the figure. Now, our target is that to establish that this minus q is the image of plus q, and because of these two charges, this spherical surface will remain at zero potential. If we can prove that, then definitely this minus q will be the image of plus q with respect to the grounded sphere. So to go forward, what we are saying is that, let's say there is a point P on the spherical surface. By the way, A is the radius of the sphere. The distance of point P from plus Q is R1. Distance of point P from minus Q is R2. Therefore, what is the potential at the point P due to these two charges? You all know the potential due to a point charge at any distance r is q by 4 pi epsilon r. This is very, very well known expression. Now, since there are two charges, it will be the addition of the two scalar potentials due to the two scalar charges, and that is given at the bottom of your screen, which is a very simple expression which you can all understand. But now we are going to impose the boundary condition. What is that? The potential of the spherical surface is zero. So we put that boundary condition. And the moment we do that, and moment we compare equation 9.9, we find that what we get is equation 9.10. And what we get is a ratio of the two charge magnitudes, that is small q by capital Q, which will be equal to, of course, the two distances, R2 by R1. Now, if I take this as a constant alpha, this ratio, and if it is constant, this R2 by R1, look at this diagram. If R2 by R1 is equal to constant, if this is the constraint, then what you get is a spherical surface. This is very standard geometry, so no big mathematics involved here. That R2 by R1 is equal to constant with respect to this diagram, figure 9.4, it's a sphere. So therefore, the problem now is, how do I find this constant alpha, so that this spherical surface is equal to the sphere of radius A, which is our grounded sphere. Now, for that, what we are saying is that let's say there are 2 points. First of all, let's join the center of the sphere, minus q and plus q. They are all on a straight line. This I forgot to tell you. This location of minus q will be on this line. And on this line, let us take 2 points, 1 and 2, on the surface of the sphere. 1.1 is towards plus q, point 2 is in the opposite direction of plus q. Now, since they are both on the surface of the sphere, this R2 by R1 is equal to constant, that I can apply. So that's exactly what you have seen here, that alpha is R2 by R1, where R2 by R1, now you can clearly see if you take the point 1, right, if you take the point 1, what is R2? This is the radius minus S, that is A minus S. That is what is written here. Then what is R1 at the point 1? R1 is distance of point P and plus Q. Now point P is the point 1. That will be the total distance D minus the radius. So here you can see. So for the point 1, this R2 by R1, I can write this. And then for the point 2, here 2, you can see now R1 will be D plus A and R2 will be A plus S, which is written here. But now both the points being on the surface of the sphere, this constant alpha being same, then this ratio must be same. So then we write this ratio must be same and we do component of dividendo. And we find very interestingly a ratio that is A by D. That is A and D, look at it. A is the radius of the sphere. D is the distance of plus Q from the center of the sphere. So first term is A by B, the second term is S by A. What is S? S is the eccentricity, that is where the minus Q is located. So you can clearly see that if I know the distance, the radius A of the sphere, and if I know the location of plus Q, therefore we know D from the center of the sphere, I can find out S. What is S? S is equal to S square by D. Similarly, what is alpha? Alpha is small q by plus q. So here you can clearly see that I can represent that alpha, which is A by D. So therefore small q is A by D into capital Q. So you can see that equation 12 and 13, the first one gives me the magnitude of q, small q. Of course, A is less than D, so small q will be less than plus q, capital Q. And then the location is given by 9.13, which is S square by D. So then my problem is solved. That means now we know what is the magnitude of the image charge and what is the location of the image charge. And please remember, we have already applied the boundary condition that phi p is equal to 0. So therefore, this spherical surface under this condition that R1 by R2 is equal to constant is our grounded sphere. That means that minus q is the image of plus q with respect to this grounded sphere. And then these are coordinate geometry, which I think you can do, 100% better than me. So you can find out what is R1 in terms of A and D, what is R2, then you can put it in the expression and you do the algebra and you get what is the pi r theta. That is the potential. And then you take the derivative, which is ER, and ER is the normal component of field intensity on the spherical surface, because you know that R component is the normal component. And then if you apply the known boundary condition of electric field intensity just of the sphere, you put it there, you can also get the what is the charge density. So this is how we get all the relevant information. But now comes our problem. What is it? That we are not having one charge and one grounded sphere. We are having two spheres. One is a live sphere, the other is a grounded sphere. This is our uh, sphere gap arrangement. And this S, in this particular case, diagram figure 9.95 is the, we call it sphere gap distance. And D is the distance between the two centers of the spheres. Now, how do we start this problem? It is something like this, that first you consider this live sphere as an isolated sphere. And you all know that an isolated charged sphere can be represented by a charge at the center of the sphere. This you have studied in your class 2. So we are assuming plus QA be the charge at the center of the live sphere when we are considering the live sphere as an isolated sphere. So that plus QA will definitely generate a spherical surface of radius A. But now I have a grounded sphere. So I have to make the potential of the grounded sphere 0. Now if I take only plus QA, then the potential of this grounded sphere surface will not be 0 if I consider only plus QA. So as per our previous discussion, we take an image minus Q1 at a certain distance S1 from the center of the grounded sphere. And we all know how to find S1. This S1 you can see at the top, S square by D. We have already discussed what will be the Q1. Q1 will be radius A by D into QA. So minus Q1 will definitely make this spherical surface as a grounded surface. But now it creates a problem. We told that when this live sphere is an isolated sphere, it can be represented by a charge at its center. But moment I consider this other charge minus Q1, then it is no longer an isolated sphere. And therefore, if I consider plus QA and minus Q1, together they will make the potential of the live sphere certainly different from V, which is violating our boundary condition. So what can I do? So what I will do is, I will take an image of minus Q1 with respect to the live sphere, that is plus Q2, at a certain distance S2, and S2 can be computed from the same expression above. Magnitude of small q2 with respect to small q1 can be calculated as above. In that case, then my plus q2 becomes the image of minus q1 with respect to the light sphere, and therefore minus q1 and plus q2 together will make the potential of the light sphere as 0. And therefore plus QA will definitely make the potential of the light sphere is equal to V. The problem is the plus QA and minus Q1 was making the potential of the grounded sphere 0. But now I have one more charge, plus Q2. So now the potential of grounded sphere will not be 0. So I will have to take another image of plus Q2 as minus Q3. Then plus Q2 and its image minus Q3 will again make the grounded sphere potential as 0. But that will change the potential of the large sphere. So we need one more image of minus Q3, that is plus Q4. And hence you can see this is an infinite process, and therefore this method is known as method of successive images. And the fact is that if you look into the expression of Q2 and so on, then you can immediately see that at every step of further successive imaging, the magnitude of the image charge is reducing significantly. And the distance is increasing and it is approaching towards the surface of the sphere. As a result, it has been established that we don't require very large number of images. So maximum, 3 images or 4 images is enough to get a quite good result of such sphere graph arrangement. So this is what is done, and this is the expression of Emax. Emax occurs at, of course, the point A and B. This can be computed. I have given you the expression. This derivation you don't require, so don't go into that. And what is the average value of field intensity? We said it is the potential difference, that is V, divided by the minimum distance, that is S. So here you can see at the bottom, average value is V by S. The maximum value is 9.19. So the field factor for the sphere gap arrangement, we can get it as this expression 9.20. And in this expression, you can see what we have. We have S. What is S? S is the sphere gap distance between the two spheres. And then what do we have? A. And what is A? A is the radius of the sphere. So you can clearly see that this is a function of the ratio of the gap distance and the radius of the sphere. We can clearly show from this that if S by A is 0.2, then this field factor is 6.8%. Is S by A is 1, it is 36.6%. And we know that if the field factor is 0 or close to 0, the field is uniform. And if it is very high, field is highly non-uniform. Now, sphere gap arrangement, the accuracy of measurement depends very much on this uniformity. And as you can clearly see that when this S by A ratio is low, we get a reasonable uniformity of field distribution. And if you recall our discussion, whatever we have told you earlier, that in the sphere gap measurement, the gap distance is always kept less than equal to radius of the sphere. Why? Because if you can see that if S by A is 0.5, then from this following table you can see that S by A 0.5, this field factor will come out to be something like 1.15. And that, oh sorry, I made a mistake. This field factor F is equal to 1 is actually the uniform. So 1.15 is around 15%. That is practically acceptable. And that is why the standards, Indian and Indian international standards, they recommend the gap distance should not be kept more than the radius of the sphere. So again, you can see that discussion that today we are doing that has very clear practical implications. It's not a theoretical discussion. A problem I have given here, what is that? Consider two spheres of 25 centimeter diameter having a gap distance of 2.5 centimeter between them. Determine the breakdown voltage of the sphere gap in air at STP. And we move in this way that the gap distance S is 2.5, diameter is 25, so radius is 12.5, so S by A is 0.2. And from the previous expression, we find field factor is 1.068. Then the breakdown will take place when the field intensity exceeds the breakdown strength of air at STP, that means 30 kb peak per centimeter. So that should be the Emax. So from there we calculate the E average in terms of field factor and Emax. It comes 28.09 kb peak per centimeter. And E average is V by S. S is 2.5. So the breakdown voltage comes out to be 70.22 kV peak. So we can clearly see that how we can get the breakdown voltage from our theoretical analysis. Moving forward, now I take another practical example, that is two long cylinders, just like our transmission line conductors. So here I am giving you an example that I have two charged cylinders, parallel cylinders, and I am taking that one has a potential of plus V, the other has a potential of minus V. So again, our target is, can I analyze this system with the help of method of images? The answer is, in this case, we don't go by the point charge, we go by the line charges. So there are two line charges we are considering. One, by the way, first we join the two axes of the cylinders, and this is the cross-sectional plane. And since these are long parallel cylinders, field is not varying along the z-axis, which is along the length of the cylinder. It is varying on the xy plane, which is the cross-sectional plane. And on this cross-sectional plane, we are joining the two centers, and the two charges are placed on this line with certain eccentricity. So plus lambda 1 is the line charge within the positively charged cylinder with an eccentricity S. Minus lambda 1 is the charge on the negatively charged cylinder with an eccentricity S. The radius of the cylinder is A. The distance between the two axes is D. And with this configuration, we are trying to prove that we can establish that these two cylindrical surfaces will be as per our boundary condition. So we start in the same way, that we take a point P on the cylinder 1, that is the positive cylinder. Then the distance from plus lambda 1 is R1. Distance from minus lambda 1 is R2. And then, as per our very well-known expression of potential due to the line charge, that means two line charges, one is plus lambda 1, the other is minus lambda 1, I can write the expression of phi p. Now, for the cylinder surface to be equipotential, because it's a conductor, as per this equation, if this has to be an equipotential, then you can clearly see that this ratio R2 by R1 has to be constant. Otherwise, phi p will not be equipotential. So what we are saying is that we are again approaching in the same way. I am considering 2 points on the positive cylinder 1 and 2 lying on the straight line joining the two axes. Then at point A1, what is the distance R1? You can clearly see the distance R1 is radius A plus S. Then at the point A, what is the distance R2? You can clearly see the distance R2 is D plus the radius A minus this S minus lambda 1, whatever the distance is. So you can see here, the first considering point 1, I write an expression for phi 1, where R2 is D plus A minus S, R1 is A plus S. Then we take the point 2 on the cylinder surface. This is the point 2. Then what is R1? This is the radius A minus S. And what is the distance R1? You can clearly see R1 is the distance D minus the radius A minus the distance S. So here you can see phi 2 is this, where R2 is D minus A minus S. This is all coming from this expression of R2 by R1. But now, since 1 and 2 are on the same cylindrical surface, so boundary condition is phi 1 is equal to phi 2. So you can see we can have the two ratios which are constant. And again, we go for the componendo dividendo and we get an expression for S, 9.31. Now the question is whether I would take positive sign or the negative sign. The answer is negative. Why? Because if you take the positive sign, then S is so high that it will be outside the cylinder. So taking the negative sign, I write 9.32 and therefore this becomes the location of the charges, which means in this diagram, this is that is the eccentricity of the location of the charges is as per equation 9.32, which you can see on your screen. And if you look at this very interestingly, if it is a transmission line, then the radius of the conductor is much higher, smaller compared to the distance between the two conductors. So D is much greater than A. And then looking at this, you can see that this S becomes almost zero. And what does it practically signify? It signifies that the line charges can be considered to be placed on the axis of the two conductors. And that's exactly how we analyze the transmission line conductors. And then we extend it, we say the potential at the point 2 on the cylinder surface. That is, of course, the positive cylinder, so potential is plus V. So I write this expression, which is, of course, already developed earlier. Here, equation 9.30. Now we are saying that this potential equal to V. And therefore, you can clearly see that I can find the magnitude of the charge lambda 1. And if you look at the right hand side, you can see this has only the potential V and all other are physical dimensions. D, the distance between the two axes, A is the radius, S is the eccentricity of the image charge. So they are all physical dimensions. So 9.33 equation clearly gives you the magnitude of the charge lambda 1. And therefore, if I consider that what is the maximum electric field intensity in this system, well, the answer is very simple. The maximum field intensity occurs at the point 2 where the distance between the two cylinders is minimum. And that minimum distance is nothing but x. And if you look at x, x is nothing but d minus 2 times the radius, d minus 2a. And how do I find the field intensity at this point? For a line charge, we all know this is q by 2 pi epsilon r. And since the negative charge is there, so we can write down the appropriate, with the appropriate signs. This becomes 9.34. And now if I look at it, we can clearly see on the right hand side that this clearly depends on the charge, potential V, then distance D, then the radius A, and the eccentricity S, which can be computed. And what about E average? E average is the potential difference, which is 2V, and the minimum distance, which is X. X is D minus 2A. So here it is that E average is 2V by this. And so field factor, it is E max by E average, and 9.35 is the field factor. Now, since it has the term S in it, and S 9.31 on your screen is in terms of D and A. So if I put the value of S, then this expression will become only in terms of D and A, that 9.35, where D and A are the two measurable quantities. That means which can be physically measured with the help of instruments. And this is very important for us because any expression, please remember, we always try to make it in terms of measurable quantities. And in this expression, D and A are the measurable quantities. The eccentricity S is not a measurable quantity. It is a computed quantity. So when we put this expression of S in equation 9.35 and you do some algebra, which you can do, you get 9.36. And now looking at 9.36, I can see that the field factor can be expressed clearly in terms of the distance d and the radius a. That's all. And it is a function of the ratio d by 2a. People have tried to modify this expression where d is x plus 2a, then putting it in this expression and doing further algebra. People have tried to develop it in terms of instead of d by 2a, instead of x by a. So this is like representing the same expression in a different form. But looking at 9.36, if it is a transmission line, once again d is much higher than a, and if you put that condition, then equation 9.36 will reduce to equation 9.38. This is for a real life transmission line. And for a real life transmission line, E average, which is 2V by D minus 2A, but A being very small compared to D, we can make it 2V by D. So then Emax, we can find out as this V by small a ln d by a. This is an expression which can be developed considering two line charges on the axis of the two conductors, and you can see that we will arrive at the same expression of 9.39. And if somebody asks what will be the capacitance per unit length of this parallel cylindrical system, the answer is capacitance will be lambda 1 by 2V, and we know the lambda 1 expression which has been already obtained earlier. I think, again, let me show you. Yes, here is lambda 1 here, 9.33 here. So lambda 1 by V I can find. So lambda 1 by 2V is pi epsilon 0 divided by ln of that. So here you can see, and then if you put the expression of S in terms of D and A and do some more algebra, you get this capacitance per unit length as equation 9.40 in terms of D and A. Some people do further algebra putting this hyperbolic expression, and people arrive at this expression which is 9.41. These are all different ways of expressing something in terms of the mathematical expression. So another problem I am giving you, this is a sort of a real life problem. Consider that a long conductor of negligible radius is at a height 5 meters from Earth's surface. By the way, this 5 meter is approximately 16 feet. This 16 feet is approximately the height of the railway line conductors that you can see everywhere. So you can assume that this is like a railway line conductor, which is a single phase conductor, and that's a pretty long conductor. Of course, radius is small, and it is at a height of Earth's surface, and it's parallel to the Earth's surface, which is just exactly the same as a railway line conductor. It has a uniform line charge density of +1 nanocoulomb per meter. This is our assumption, of course. Find the electric potential and field intensity at a point 3 meters below the line. So figure looks like this, where you can see this black dot is the conductor with +1 nanocoulomb per meter. Of course, we have to take the image, that is -1 nanocoulomb per meter. Of course, this is not an image with respect to the cylinder, it is image with respect to the Earth surface. So it will be just a standard image, that is image will be equal to and opposite to the actual charge, and the height and the depth with respect to the Earth will be same. So height and depth both being 5 meters, and the distance of that point is just below the conductor 3 meters. So the height of the point P from Earth's surface is 2 meters. That means roughly about 6 feet. That means a person standing here of a 6 feet height, so this point is right on his head. So basically what we are trying to compute is that there is a single phase railway line conductor running, and one person is standing just below it, a 6 feet long height man or woman, and what is the potential or field intensity at his head. So here you can see lambda 1 is given, then R1 and R2. R1 is the distance for plus lambda 1, so that is 3 meter. R2 is the distance from minus lambda 1, which is 5 meter, plus 2 meter, 7 meter. So you can find out the expression of potential, which is in terms of ln R2 by R1, already stated earlier. So potential is 15.23 volts. And then electric field intensity, if you write the expression for exp by taking the derivative of phi p in terms of x coordinate, it will come out to be 0, which is quite obvious because this point P is along the line joining the two charges. So the x component, which is the horizontal component, has to be 0. This is quite obvious. But the vertical component, that is the y component, so that will be of course there, and we can find out that has minus 8.56 volts per meter. Now this 1 nanocoulomb per meter is not known what will be the exact value, but even for this very low charge density, you can see there is a 15-volt potential right on the head of that particular person. And 15 volt is not a small value. So if somebody is just walking down the railway line, not a major issue. But you know, in India, a lot of people just sits on the railway track and others. And so they are continuously exposed to such potentials arising out of the electric field. And that will have some effect on the long run, but people will not understand that this is coming from the effect of the field. People will think this is something different. I have this disease, I have that disease. But this is actually the biological effect of electric field. And in the Western countries, people take this very seriously, and therefore taking an overhead line through a crowded place. This is called the right of way problem. Right of way problem. This is a big issue in all the Western countries. In India, this right of way problem comes from a separate concept, not from the biological effect, but that is from the money issue, that I will give land, so you have to give us money. So in India, the problem is different. Nobody is bothered about that. What is the effect on our biological system? But this problem just goes on to show it once again, to tell you that this is not just a theoretical problem. As I said, this is just like somebody 6 feet high person standing below a railway track. What will be its biological? What will be its field effect on our biological system? Problem another one. Determine the breakdown voltage in air at STP of a 20 centimeter diameter cylindrical electrode placed horizontally with its axis 20 centimeter above the Earth's surface. Now here it is not two cylinders we are saying, but since we are saying Earth's surface, so naturally there will be an image of that. So it will become a parallel cylindrical system. So this is shown here. So top cylinder, of course, this is the cross-sectional diagram. The top cylinder, since the diameter is 20 centimeters, so radius is 10 centimeter, and its potential is plus V. And its axis is 20 centimeter above the Earth's surface, so the axis of the image will be 20 centimeter below the Earth's surface. So the distance between the two axes, that is our D, will become 40 meters. Radius is 10 meters, so D is 40 meter, radius is 10 centimeter, sorry, 40 centimeters. There is a mistake here, sorry. Here all are written in meters. Actually, they should be in centimeters. That's a mistake here. So we can find out what is the field factor F. and it comes out to be 1.315. Then when the breakdown takes place, of course, the field intensity is equal to the breakdown strength of air at STP, which is 30 kg peak per centimeter. So we find out E average, which is E max by F. It comes out to be 22.81 kV peak per centimeter. Then what is E average? It is 2V by D minus 2A. So 2V by D is 40 centimeter, 2A is 20 centimeter, 2 into 10. So it is 2V by 20. This is equal to 22.81. So the breakdown voltage is 228.1 kV peak. So this cylinder, which is 10 centimeter radius, placed at a height of 20 centimeter from Earth's surface, will break down at 228.1 kV peak, which we can determine from the analytical analysis that we have discussed today. So today I have tried to tell you that there are two practical examples. One is a sphere gap arrangement, and the other one is the transmission line conductor system or the railway conductor system. How we can analyze or get results of such problems with the help of analytical solution, that is method of images. So I think that is from my side today. If you have any questions, you feel free. Any questions? Otherwise, we will call it a day. Okay, thank you. So today, then the class I am concluding, and what we have discussed earlier, our next class is
24.
27th. Correct, 27th. Okay, so thank you. All the best.
Thank you, sir.
Thank you, sir.